Microphone test, test, test. Okay, hello and welcome to the live. So yesterday I swapped out the convolutional blocks from my autoencoder and replaced them with transformers. So this is vector quantized, and there was an issue with training because the perplexity was very low. It didn't make use of the codebook entries. But I realized I probably need to add positional embedding because I'm splitting up the image into 4x4 patches. So now I just want to add 2 more channels to the input to make it 5 channels. So one channel will be the x coordinate and the other will be the y coordinate from -1 to 1. And I hope that in this way the transformer blocks will pick up something more meaningful. So let's call it input, because it's confusing when you have coordinates and the input is also called. So we have px lint space in this shape. So there are 2 batches, 2 channels, and the 4x4 image in this small example. Let's make it 1 channel and 3x3 like this, and py also yeah, but this also looks like the x. So let's self is 4D. Yeah, so this is the y coordinate then, and it should work as well with multiple channels. So I want to concatenate this along dimension 1 with the input to have 5 channels. So out becomes torch.cat imp px py on dimension 1, and let's also print out.shape and out itself. So this is the x, this is the y, this is the actual image. So I believe we are good to go, and I should find my phone, but I don't have it with me. So anyways, we can take this function and use it in our encoder. Let's try our encoder. Got tensors on the CPU because these are not on the same device as the input. So in this case, is there a device? Yes, device parameter should be the inputs device to be on the same. Still an issue because given groups equals 1, weight of size expected input to have 5 channels but got 9 channels instead. Okay, well, worst case we can print everything and see how it gets 9 channels. So the input image has 3. Maybe I should use stack. Well, it looked fine in the example, so let's just print x.shape and x, debug a little. Of course, this is huge, but it has 9. Now it has 3, but this one's 5. So for some reason, here it works nicely. It's because, I guess, the expand as the input. That's the issue. So I only wanted to have this, because it adds, this becomes 6, so yeah. What we can do, since this is our input shape and we know that, expand batch 1 HW, but put it in a tuple. Now it's nice. So going back here, now it got 3 because I need to uncomment this. Okay, this one looks good. Except we don't need to print this anymore. Seems to be compatible. So our model has 200,000 parameters on a small data set of faces. Just make it print more nicely. Training loss is growing and perplexity is really low. That's not going to work at all. So what DALL-E does supposedly is that it replaces unused codebook entries with outputs from the encoder. But I'm not sure if that would work here, if the encoder itself cannot fight its way with the, I mean, it's a single convolutional block, and there are no overlaps between the patches, which is, it's weird. I would take more convolutional blocks. And then use that with the transformer, or double check my implementation of the transformer. So let's do this a bit differently. Let's take the original encoder without transformers, and I already know that it reconstructs pretty bad images. So what if I just add a few transformer blocks in the end, but the problem with that would be that the image is already very downsampled. So maybe just downsample. It says right now 64 by 64 images. Yep. So what if we downsample? We have this residual downsample. This just kernel size 1, stride 2, and normalization for the skip connection. So I would use then I will need to reinstate the channels, alright, probably. Nope. Just quickly do it like this. South dot. Well, that's that becomes the conv as an nn dot sequential. And I will provide the channels here as 5, 64. So that's one downsample. So it becomes 32 by 32. And here the kernel size is 3 with a stride 2. So there are some overlaps. And downsample it once more with 128 channels. And this returns X as B channels HW, and the transformer block, don't need this anymore, wants it as BTD. So here's, we embed the position, we run it through the convolutional downsampling. The channels in the last, this should be D in the end. And so this is 32, 16, it's gonna be 8 by 8 already. Let's try. Then we have 8, 8. We could downsample once more to get 4 by 4 patches, which is just according to the DeepMind paper. They say 4 by 4 patches, but I think they don't specify whether those patches are just from the image. So the image is split up. Batch size, the batch size 4. I was doing some digging with ChatGPT, but I think it completely misled me, because it hallucinated that with batch size 4 they just split up the images into 4 sized batches. I'm not sure for vision how that would work. I mean, based on my experience with that, it doesn't. So let's have a convnet, 5 channels with positional embedding. We downsample to 4 by 4 patches and latent dim number of channels. Then squash the patch into this shape. And apply the transformer blocks as many times as we have num layers. So let's take the same way the residual upsample block from the previous model. So in this case, from latent, transformer blocks will run that. Now it gets reshaped, and it should be 4 by 4 here. So let's take these channels. reverse it. So we start from D and arrive at actually 3. So D times 4 by 4, it becomes 3 times this. And well, channel 0 is actually D in my example. So when I copy this, I don't need this one. And in the last layer, no skip connections, just a convolution and a sigmoid. Now this runs through the channels pairwise, but it skips the last pair. And the conv transpose has a kernel size of 4. All right. Encoded is 4 by 4 with 5. Yep, that works. This seems to work. Now 32 latent DIMMs. Not much entropy here. I mean, it's just faces, so we could try with 32 dimensions. The codebook just 64. And just let's just put one layer, just one transformer block with the default beta, and we will compare it. If it converges at all, we will compare it with this. Doesn't look like it's using the codebook so much. But train loss is converging so far from 1.7 after 10 epochs. Okay, we can run this for another 500. So in this case, this was a 128 image size, and these were the channels. So 64, 32, 16, 8 by 8, this went down until 4 by 4. That's, I don't know. It's too small, I think, for maybe not. but it didn't yield good results. Well, 26, the perplexity looks good because we have 64. Not so great, but at least it's around, what, 40% of use. That's better than 4% of use, as it was before. And the learning rate is pretty high, so I might try to adjust that. Let's see another 50 epochs. Evaluation loss is much better than the training loss. Let's go another 250. So perplexity is growing, I like that. And the train loss, well, very, very slowly, but another 250 with a dropped learning rate. But it's here, it's defined here. So I cannot change it without actually reinitializing the model. This should come here, by the way. So this logs the total epochs. And another 250. I would like to see a perplexity of at least 50 plus. Just to be sure we use most of the code book. Well, it's getting there. That's good. The loss isn't so good. Maybe we could do more with a reduced learning rate. This was a good one. And I'm also adding some noise to this image, 7% noise. Another thing I could do is that I don't add the positional embedding right in the beginning, but add it to the latent using frequencies. Training wise it looks okay with an L1 loss, but I fear that the reconstruction quality will be terrible. Oh, come on. It's almost 50. Bump it up over 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. 50. Yes. And this is going to be pretty much it. I don't expect any more meaningful convergence. Training loss isn't getting any lower. So this was one with the transformers, but without the multi-layer convolutions. And this is just so bad. Jesus. I don't think that the transformers here help at all. So this is a sample implementation. I just find it hard to believe that transformer is so bad in this case. Did I miss something? No, I don't need this. I need GPT-2 here. Here I use dimension 1. This is -1, which is this t. So I'm soft maxing on the wrong dimension. Doesn't look like this helped anything. Maybe I could bump up the learning rate even more. I mean, it looks a bit better, maybe. Interesting. Let's try bumping up the learning rate. And I would split the model declaration into another code block. Reinitialize the model with let's make it a huge model. 4 transformers. This many latents. Codebook. 27 million. Way too much of a complete overkill. I could probably initialize the codebook better because it's initialized with a uniform distribution, but that doesn't seem to work very well with the transformers. So transformer outputs are non-Gaussian, highly structured, and often clustered early in training. And because of that, of course, the whole codebook needs to move a lot with uniform distributions. So when using transformers, yeah, this is a good idea. So run the encoder for one epoch or at least gather some outputs from the encoder, and then set those as your initial codebook weights. So this again won't look good. Yep, oh my god. 4 eyes. And it looks like a man. So because transformer outputs are structured in the latent space, the uniform init doesn't work well. Hence, when running the training, I would take random samples from the encoder for a while. And the codebook size is 512. Hey, this should be, oh, because I copied it from here, so it's learning on the, Jesus Christ. That's why you should either not copy your code or double check, because it was training on the test set all along. So let's not take random samples, let's try and train it on the train set. I didn't not reinitialize my model, but still this doesn't seem to work that well. So let's try sampling for X in data train. Let's disable the noise addition and take this init codebook based on encoder samples. So I have the image. I will just call model.enc, which will return only the Z. And we store that. We don't need a loss here. Now let's take the model VQ codebook weight .data.copy from samples, and we take the samples let's call it, I will wrap this in a function. And the samples will be I should make the latents. We can call now latents. The latents here torch dot stack maybe sequence of tensors to concatenate a sequence of tensors along a new dimension, and they need to be the same size, okay? And the default dimension is 0. So from latents torch.run perm, which returns a random permutation of integers from 0 to and -1. It's len latents. And I pick the first. It's stored as model.k or model.vq.k. And let's call this function. I'm just going to restart the kernel, exit the training. Now we can rerun everything before. Now actually, since I use this code piece for retraining, I will init the code book in a previous block. Here. But it left the GPU memory full, even though I restarted the kernel. Yep, GPU memory is full. But now it's wiped. Good. Why? I'm just storing 5,000 latents. And it allocates 15 gigabytes of GPU memory. What's so big? probably allocating something way too much somewhere. So that's around 5,000 times 4 by 4 times this. I mean, it stores a batch. So could still work. Now this I can do, so well, I could iterate over the first dim of the tensor, and for simplicity let's just do that for let's call this, yeah, whatever, ZZZ in Z, and ZZZ. Okay, that's fine, and 251 won't. I mean, so K is 512, so this should only run twice. Because this breaks only from here. Okay. Could out of memory. I definitely don't need a new dimension, so cat. I can just push here Z to the latent, the batch. It's going to be easier. But then len latents times batch size. Now I'm again out of memory. Before we execute anything, return. Okay, so far so good. Now samples. Yes, and let's print the code book is of DK. So that's D, that's K. But these are 4x4 patches. So I could reshape probably. So if I view this as, let's make it codebook white model.vq codebook white, and there's, well, that's just DK. What I need is the samples actually. Samples.shape, and this will become batch DHW. And I could do this here, latents. Equals. Because I have a D there as well, so make it D. Well, then view it as B, HW, that. What the fuck? Oh, this one. So this can be that. And now I have, this is the code book. Those are the samples, so it should be ready to be copied. This way, perplexity starts around 100 and something, which is much better than before, but like we have 500. I mean, it's so much better. But the train loss is not better that much, just because we use more entries from the code book. And now I am not adding noise to the input. %, noise might have been much, but yeah, so if you use transformers in your encoder, then you shouldn't init the codebook with uniform distribution, because the transformer output is already much more structured than uniform, even without training. I don't know. L1 loss. But I'm only keeping track of the total loss. And now this is a huge network. For 250 epochs. Maybe I could take the model, disable vector quantization for the first 50 epochs, so that the transformers already start to converge a bit, and then enable it initialize the codebook with those outputs of the encoder, and that might even give better coverage, and then train the model further with it. That's pretty good. That's pretty good. We won't achieve this quality for sure because this is not converging that great. With the mean square error, I would probably get the same or even more blurry image, but so what to bump up is the question. Well, the codebook is not heavily used, many dead codes. And the convolutional neural net, well, we downsample to 4x4, so there's a bottleneck of information. 4x4 times 128 in the last convolution layer. So that bottleneck might be the reason that we cannot pass through more information. So I would try to bump up the latent dim to 256, and we'll have an 8 million parameter model. But structure-wise, this looks pretty good. Like the shapes resemble the hair. To me, that tells that the transformers can extract enough information. But what if I completely keep the same? I completely disable the transformers. I might need to change the implementation, because if this is 0, it passes to the encoder and decoder. In self.blocks, this will be 0. I'm not sure if I messed up something. Let me just restart the entire notebook to be sure to wipe out everything and run everything again. No transformers now. It's just a pure vector quantized autoencoder. The codebook is initted from the encoder, the first encoder output. Just running it for 250 epochs, and well, this had no transformers, and this was the result. Of course, codebook initialization here was uniform, but without transformers, that's basically a standard init for the codebook. Perplexity was okay. 512 codebook size, 3.5 million parameters. This is much smaller, and this one has positional encoding. So, but the rest is the same. And the dimensions here, it was only 32. So if I set the device to torch.device CUDA1, .350 and 128 parameters. This uses the faces 128. Let's change it to the 64 variant. And I'm moving this out from here. Run this as well. Yeah, this won't work. What? So now I'm training one model on one GPU and the other model on the other GPU. So the difference, again, this has a codebook in it of uniform with mean square error loss. This has no transformers, no positional embedding. I mean, I would like to see how much the positional embedding helps the model, so it should be L1 loss as well. And a few other changes, I think, because this also uses only Adam and no weight decay. So there are many hyperparameters to play around with, that's for sure. So whoa. So without transformers, and yeah, it's apparent. It's much more blurry. So let's bump up the dimensionality to 256. Encoder maybe 2 transformers, 3 transformers, and the decoder to have 6. That's a huge model because of the D. And the codebook use for this one was 300. I could maybe lower the codebook size to 384. Doesn't really help with that. Okay, it's a big model, but at least let's try if we can get good reconstruction. Simple L1 loss. There's definitely space to improve the reconstruction loss. There's so-called perceptual loss, but it's based on the VGG architecture. And I don't know, if, using another pre-trained neural network to train my network kind of feels like I'm not doing the job really well. I know you should stand on the shoulder of giants, but it kind of feels like cheating, because I could just use like a stable diffusion or something to generate the loss, or just use stable diffusion decoder to decode the samples. That's not really my work then. The structural similarity measure index I can still accept with its convolutions. So structural similarity measure, aka SSIM. So SSIM creates a convolutional filter with the Gaussian bell curve in 2D. And convolves multiple versions of the image with it, and there is a formula. It's implemented in scikit-learn as well, ScienceKit. So it compares luminance, contrast, and structure. This basically measures the mean brightness of both patches, 11 by 11 typically. So X is one image, Y is the other. The mean of patches plus some C1 constant to avoid divide by 0. Compares local standard deviation. And structure measures how two patches textures align using the covariance and the standard deviations, and then they are ANDed together, multiplied together basically, and simplify. This is a big ass formula. When broken down into these, it's much more understandable, but this is probably faster. And again, you have to implement this using PyTorch and tensors. So the SSIM score of 1 is a perfect match, which means we have to negate this. Yeah, it's in this one. So next I'm gonna try and use that. Okay, this loss looks much better with bottleneck now widened to 4x4 times 256, and the decoder bigger than the encoder, but it's still blurry. It's not so crispy. But it was only 250 epochs. So let's try a SSIM. Could not be resolved. I'm completely sure I used sklearn.image or matrix import. So sklearn.metrics plot. Nope. Okay, Google search. But I would need a PyTorch impulse. So ChatGPT came up with an implementation since results are not guaranteed. I'm going to copy paste that here. And I'm going to use this one instead of implementing it and learning it. So reconstruction L1 plus 1 minus ssim and C. Yeah, but this compares only a single image. And now this implementation compares a batch of images and takes the mean of those. I might want to change this to mean dim to a sum, but by default it averages, so, and it returns this. This should return a number if it's averaged, right? We will see. It will throw an error anyway, so compare y hat with x, window size 11, average it, try to run it. Input. Yeah, well, it's ChatGPT, so there was it. Add the exponentiation and create a window. 1D Gaussian window. Create window. This takes a float, sigma. Well, I should be able to multiply a tensor with a float, but the argument of the exponent must be a tensor. But I did not initialize the model. Okay, restart kernel, free up GPU memory, and rerun everything. Now here, what did I change? I upped the dimensionality from 32 to 128, trained it for 250 epochs. The train loss is much smaller than our transformer model. But the image is crap. Because it's mean squared error, so that tends to make blurry reconstructions. Okay. And taking a break. I might come back or might not come back. So, cheers.